represents the full T00. Now we are going to apply separate conservation law on each of these. And the general conservation law, let me remind you, takes the following form: rho I A cube plus 3pi A dot A square equal to 0, where I can be either matter or radiation or cosmological constant. So let's start with matter, I equal to m. That's the simplest case. So d dt of rho m A cube is equal to 0. Okay, because Pm is 0. So this tells us that rho m should go as 1 over A cube. Okay, rho m A cube is constant. So I will write this as rho m naught times A naught cube over A cube. Okay, this is the initial condition. So this is the density today. So that at T equal to T naught, this is 1 and rho equal to rho m naught. Okay, that's the initial condition. And this is what we get. PR is rho r by 3. So we can write this as d dt of rho r A cube plus 3pr will now be rho r A dot A square is equal to 0. This you can check, can read it as d dt of rho r A to the 4 equal to 0. Okay, just multiply by a factor of A. Okay, and this to combine into d dt of rho r A to the 4. So this tells us that rho r should fall off as 1 over A to the 4. So rho r is given by rho r naught times A naught to the 4 over A to the 4. Finally, for the cosmological constant, P lambda is minus rho lambda. So you have d dt of rho lambda A cube is minus 3 rho lambda A dot A square. So this essentially tells you that d dt of rho lambda is equal to 0. Okay, if we just expand it out, the rho lambda times 3A square A dot just cancels. This is plus, minus this is equal to 0. Anyway, this is the equation that we have here. So rho lambda is equal to rho lambda now. Is this okay? So now let's substitute this back into the Friedmann equation. We get A dot over A square plus K over A square as 8 pi g over 3 times rho m naught A naught cube over A cube plus rho r naught A naught to the 4 over A to the 4 plus rho lambda. So the idea now is that this equation we think of as a differential equation for A dot and solve it with the appropriate initial condition. Okay. The initial condition is provided by the value of each Hubble constant today, okay, because that tells you what the rate of change of A is. So if you know rho m naught, rho r naught and rho lambda naught, you can solve this equation in principle. Is this clear? Now it's convenient to not work with A, but this quantity lambda, which is A of t over A naught. Okay, because you don't know what A naught is. But lambda by definition is 1 today. Okay, so that gives the initial value of lambda and then you can start evaluating from there. So we'll just write down the differential equation in terms of lambda. Okay, because that makes things a little more transparent. So A dot over A is just lambda dot. Sorry, A lambda dot over lambda. Okay, because it is just scale. So A dot over A is lambda dot over lambda. So you can write this equation as lambda dot over lambda square plus k over A naught square lambda square equal to 850 over 3 rho m naught by lambda cube plus rho r naught by lambda 4 plus rho lambda naught. Then this equation takes the form half lambda dot square. First term is half lambda dot square plus k over 2 A0 square. Okay, the lambda square cancels with lambda square, but there is a 2 sitting here. And now I am going to take this on the left hand side. So I will write this minus 4 pi g over 3 rho m naught. We are multiplying by lambda square. Okay, half we have used here, but lambda square will be multiplying the inside. So this becomes rho m naught over lambda plus rho r naught over lambda square plus rho lambda naught times lambda square. This should be 0. That's it. Is this clear? So let's call this whole quantity some function v of lambda. Now we'll see that this equation now half lambda dot square plus v of lambda equal to 0. This you can think of as the equation of motion of a particle. If you have a particle moving in a potential v, the total energy is conserved, right? So you can start with Newton's equation, but you can integrate it once. Total energy is conserved, so you get half mx dot square plus v equal to a constant. Okay. M here is 1 because there is no m sitting here. V is this, and the fact that you have 0 on the right hand side means that we are talking about a zero energy particle. Okay. So you can think of this as if it's a motion of a zero energy particle in this potential. Is this clear? So to study qualitatively what the motion will look like, you have to just plot the potential and see what it means for the motion. So V versus lambda. Now, of course, to plot it, to understand qualitatively, we need the values of all of these. Okay, but right now we don't mention what those values are. Okay. But there is one detail that we'll be using. Okay, later on I'll explain how experimentally this conclusion is reached. Okay, experimentally, of course, we have knowledge about all of these constants. Okay, but
A0 is not.
We'll discuss. So the point is, what we know today is that this term is consistent with 0. Okay, this is that within experimental accuracy, okay, there is no evidence that this is not 0. Okay, which basically means that A0 is very large. Okay, how large we can discuss later. Okay. But this means that in studying qualitatively the behavior of the motion, we can basically set this equal to 0. Okay. If we set this equal to 0, then we see that the potential, which is this, is always negative. Okay. Furthermore, the potential goes to infinity, minus infinity, as lambda goes to 0. That's from the radiation term. Okay. So it goes to minus infinity as lambda goes to 0, and it also goes to minus infinity as lambda goes to infinity because of this term. And we know that today lambda is increasing. Okay, that we discussed. Okay, because of the rate shift, we know today lambda is increasing, so lambda dot is non-zero and positive. So it's clear what's going to happen, right? The particle is going to basically move along this axis forever under such a potential. Right? In fact, it will accelerate more and more as once you cross this maximum, okay, it will accelerate more and more with time. And from the data that we have today, we know that we are past the maximum. Okay, so it is really accelerating. Okay, because if you are below this, okay, then you will be decelerating, right? Because the potential is going up. Okay, you start accelerating once you have crossed this line, and you know that today the universe is accelerating, so you are somewhere here.
So earlier you said that today the universe is decelerating.
Well, I introduced the decelerating parameter Q naught, right? But then I said the Q naught is negative, right? That's why it's accelerating. Is this clear? Now, this is very different from the situation that was there 20 years ago. Basically, the difference has come from the fact that 20 years ago, one didn't know the existence of this rho lambda 0. So let's see what will happen if we had rho lambda 0 equal to 0.
So when we put the first term to 0, that k by 2 a naught square,
Yes.
then we are assuming that k is also maybe 0.
Well, k could be 0, but it's indistinguishable from a naught being very large. Because in all physical quantities, it's this ratio which will appear. Okay. So basically the point is a naught is very large. Okay. That means that the sphere that we had considered has a very large radius today, right? That's indistinguishable from flat space. So k equal to 0 represents flat space. K a naught very is large, okay, means that it's a sphere of a very large radius. And clearly these are not distinguishable. Okay. A sphere of a very large radius or a hyperbola of a very large radius is like that, right? So experimentally you can only rule out, you can put a bound on how low the radius can be, right? By examining your local neighborhood, right? You can never say exactly whether it's 0 or not, right? And that's the situation. Okay, now if this is 0, if rho lambda naught is 0, okay, see that the low lambda behavior, lambda goes to 0 behavior of course remains the same, right? Because that is dominated by this. But as lambda goes to infinity, this term goes to 0, right? And there, what will happen in the future depends crucially on this term. Because however small this is, as lambda goes to infinity, this is going to become important. Is this clear? So, if rho lambda is equal to 0, then there is qualitatively different behavior, like I said later time. So, if k is greater than 0, the potential approach is positive constant at infinity. Okay? Now, it is clear from this picture that the universe will always be decelerating, right? Because the potential is going up. Okay, and that's the reason why people introduce the deceleration parameter rather than the acceleration parameter. And it's also clear that eventually, okay, the point if k is very small, then this becomes this meets the real axis for a large value of lambda. Nevertheless, eventually the expansion will turn back, right, for positive k if k is equal to 1. So this is the case k equal to 1. K equal to 0 or minus 1. K equal to minus 1 is given here. It approaches this, but it approaches finite value. So then the universe keeps, so here it will turn back, there it will keep moving.
So here the total energy is 0.
Total energy is always 0 because the way you have set it up, right, the right hand side is always 0. Right? So basically that's what sets the constant p. So total energy you cannot change in this notation. So k equal to minus 1, it will go on forever, and k equal to 0 if the universe is exactly flat, then it goes like this, asymptotes to this, and then also then again you can check that basically the universe expands forever. Okay. So before the discovery of the cosmological constant, okay, k had an important role to play because the final fate of the universe would have been decided by whether k is 1 or minus 1 or 0. But after the discovery of the cosmological constant, that is not relevant anymore.
So what is the difference between k is equal to minus 1
k equal to minus 1, it approaches minus 1 here. So the velocity approaches a constant, right? The expansion rate, lambda dot, approaches a constant value as t goes to infinity. Here, lambda dot goes to 0 as t goes to infinity because the energy, the total energy is becoming equal to potential energy. Right? So the half lambda dot square approaches 0, but nevertheless it keeps expanding.
So, and if k equals to 1 and there is cosmological constant, then it may happen that this curve may cross that 0 line.
Yes, it may happen that it crosses that 0 line. Okay. But as I said, from the experimental fact, we know that this is very small. Okay, this is unobservable today. Right? So which basically means that these will always dominate over this. But yes, if this happens, then there are two possibilities, right? One is that the universe goes like this and bounces back. This is one region. The other region will be that we are here, in which case we will bounce back and keep expanding.
And in this case, there is no going to that 0 also.
Yeah, if you come from outside, right, you don't go to 0. You bounce back at some critical point, but you can be here. Right? In which case you expand and then eventually you come back.
So two disconnected.
Exactly, two disconnected branch of solutions.
This case is for what? K value?
No, he is saying that in case if k was not so, if this k over a naught square term was not so small, right, then it could have happened that somewhere in the middle the potential becomes positive. Right? So this is when k over a naught square is significant. Okay, then this would happen. Is this clear?
So, but if we think about it, G we know is not a quantity which is very large, and rho m naught, rho r naught, these are the densities at present day which are also
Not very
apparently
large,
small.
yes.
So, the whole quantity seems small at its lowest limit. So, how can you be certain 100% that this k by 2a naught square is smaller than this one?
Yeah, so I'll discuss how this is measured, then it will become clear. Right? That why this is small. Yes, it's true that these are small, but A naught is so big that it basically overcomes that smallness. Right? But we will discuss soon how we determine this. Okay, and what exactly one means by k over A naught square being small or large. Okay, but before we do that, let me just discuss some limits. So, late time, we know that this is dominated by cosmological constant, right? So, late time, large time, the equation is half lambda naught square minus 4 pi g over 3 rho lambda naught times lambda square equal to 0. So this will give you lambda dot over lambda as 8 pi g over 3 rho lambda naught square root. So you can easily integrate. Lambda is equal to some constant k, or like the exponential 8 pi not times t plus some constant. Right, I just integrated this. So basically what I said is at large time we know that lambda is increasing, so this is the dominant contribution. Okay. I ignored these terms, and that's the solution to the differential equation. So late time, when all the other components have become small, cosmological constant dominates, then the universe will expand exponentially. How this is bounced back? Oh, because this is a potential, right? And the particle has zero energy, right? So if it reaches, if it comes like this, right? At some point, the energy will become equal to the potential energy, right? So in this, right? Because energy, total energy is zero. This is the potential energy.
So this is going to be your V of lambda versus lambda.
Yeah, this is V of lambda versus lambda.
So at lambda tends to infinity, there is a k by 2a square term.
That is
Yes. So that's this one,
Sir.
right? So this is this k over 2a0 square. Okay. But the particle is moving with energy zero, right? So in this region, okay, the potential energy is k over 2a0 square. Kinetic energy must be minus 2 of k over 2a0 square.
It cannot happen.
That cannot happen, right? So that's why this you cannot cross. Once you reach this, so in any region here, the kinetic energy is negative. Okay, so that cannot happen. So it has to bounce back. Right? But here, of course, that problem is not there. Right? Kinetic energy always remains positive. Okay. Early time, lambda is small. So there, the radiation term dominates. Yeah, because this goes over 1 over lambda square. Okay, it dominates over the others. So we get half lambda dot square minus 4 pi g over 3 rho lambda naught rho lambda r over lambda square equal to 0.
So rho r naught.
Rho r naught. Thank you. Rho r naught. So multiplying and then taking square root, we get lambda lambda dot as 8 pi g over 3 rho r naught to the power half. So you can easily integrate this. Half lambda dot square is 8 pi g over 3 rho r naught to the power half times t plus some other constant c2.
So lambda square.
Sorry, lambda square. Thank you. I just integrated this. So this tells us that lambda is 2 to the half times 8 pi g over 3 rho r naught to the 1 quarter t plus c2 to the power half. Right? So you see the lambda of t is equal to 0 at t equal to minus 2. This is a singularity. Okay, you can easily check that if you take the metric that you had written down, where lambda multiplies the space part, and if lambda goes to 0, okay, then basically you get curvature singularity. So there is no way to change coordinates to remove these singularities. Okay. So this is a singular configuration, and this is what is called a Big Bang singularity.
So when we see back to
Pardon?
when we put the value of lambda to c,
Yeah, if you just put t equal to minus c2,
no, the lambda will be 0.
yeah, so you take the metric, right? From the metric you can calculate the Riemann tensors, right?
Yes, yes.
And the curvature scalars, various scalars out of the Riemann tensor. If those diverge, then you know that there is no way to change coordinates to make this non-singular, right? And that's what will happen here. If you calculate Riemann tensor and take appropriate combinations of the Riemann tensor to make scalars, you will find that at t equal to minus c2 they all diverge. Okay. So conventionally, one shifts the origin to take this to be t equal to 0. Okay. So convention is that t equal to 0 is the time where there is singularity.
So the present time is
Present time is today's. We will discuss the age of the universe. Right? So starting from Big Bang, you can calculate the value of t today with this. So once you have chosen the origin of time, you fix. There is no further freedom, right? Then you should be able to calculate what the present time is, right? And we'll see how to calculate that. Is this okay? So this is the definition of the origin of time, right? Because otherwise, of course, time you can always translate, right? There is nothing which tells you what the origin of time is. Okay, but we define the origin of time as the location of the Big Bang singularity. Now, there are of course, not everything about this formula is not correct. Okay, in particular, this rho r naught that one will have there, okay, really at the time of singularity, is not the same rho r naught that we measured today. Okay? Because this formula assumes that the energy density in radiation is not exchanged with anything else. Right? We have assumed that full non-interacting matter and radiation, so on. But in the intermediate stages, okay, there is interaction between matter and radiation. In fact, there is, as you go to higher and higher temperature, okay, we will see that later on, that this also implies that temperature is infinity at the Big Bang singularity. But basically, as you go to higher and higher temperature, more and more matter becomes non-relativistic and energy starts getting become relativistic and energy start getting exchanged between what would have been matter and what would have been radiation. Okay. So this is some constant which you can calculate in principle, okay. But this is not what rho r naught you calculate today. Okay. What doesn't change is the fact that it blows up at some point, okay, or this lambda goes to 0.
Sir, near singular point, how do we say that the metric will remain homogeneous and isotropic? Means all
Yeah, so of course we don't know, right? So we don't know what exactly happens at a Big Bang singularity.
So this calculation, how can we continue up to the singularity?
Yeah, so you are not going to continue to up to the singularity,
Just
right? But just before the singularity, or when the quantum effects are small, we can trust this, right? So all it says is that if you just follow the classical evolution, then that leads to a singularity. Yeah, and then you can see that if there is a way to resolve the singularity by other means.
Sir, but if you supposedly if you solve it for say a non-zero rho lambda naught,
Yes.
would you still get a singularity?
Yes, because the point is that when lambda becomes small, then this is irrelevant, right? See, all you have used here is that for doesn't matter what these constants are, as long as lambda is small enough, if there is any radiation component, that will dominate. And that's what you have used to solve this.
If we solve without approximation, we solve it exactly.
You will get the same singularity because after all, approximation is supposed to represent the exact physics near that point, right? So what I am saying is rho lambda naught, because this is subdominant compared to this, existence of these will not help us in resolving the singularity that comes from lambda equal to 0.
So you are solving this problem here lambda equals to 0.
Yes.
So but it might also be the case that your system has started from a situation where lambda was not 0.
Yeah, but then we have to make sure, explain why, how, right? See, if the system might have started from a place where lambda is not equal to 0, right? But if you follow these equations, there is no such starting point, right? If these are the equations that you have to solve, you can continue backwards. Right? You cannot simply say that the system started from t equal to c1 plus some fixed number, right? Because then there must be some physics which tells you why this equation breaks down. Right? In the absence of any new introduction of new physics, this is what will happen. And that's what this is saying. Okay. Now, for completing this analysis, okay, let's also discuss what would happen if in some region matter dominates. Now, we don't know as yet whether there is any such time period of the universe where matter dominates, right? Because for matter to dominate, this term has to be larger than both this and this.
In the intermediate space, when what happens?
Well, it may happen, unless I tell you what these values are, right? It may happen that by the time this has become smaller than this has become larger than this. Sorry, by the time this has become smaller than this has become larger than this. That can also happen, right? But we will see that later when you actually give the values, that indeed there is a window where this term dominates. Okay, where this is larger than this and also this is larger than this. Okay, right now we don't know because I haven't told you what these values are. Okay, but let's just go ahead and see anyway what happens if the matter term dominates in some window.
So matter domination is very sensitive to the constant.
Yes, matter domination is, whether there is any matter dominated era is sensitive to the constants, right? Which is not true for the radiation or cosmological constant. Because you know that whatever be the mixture, sufficiently far past, right? When lambda was small enough, radiation will dominate. and sufficiently far in the future, cosmological constant will dominate. Whether matter dominates in any period, okay, depends on the values of these constants. Right? If these two constants are very small, then obviously there is some window where this term can be larger than both of these. Okay, but so let's just go ahead and study this anyway. Okay? Even though at this stage we don't know whether it's relevant for physics or not. Okay, but since you have the equations, it's not hard to solve it. Let me do it here. So matter dominated universe will involve half lambda square minus 4 pi g over 3 rho naught over lambda
Dot.
lambda naught. So again, multiplying and taking square root, we get lambda to be half lambda naught is equal to 8 pi g over 3 rho m naught half. So you can integrate this. This gives you 2/3 lambda to the 3/2, right? Is 8 pi g over 3 rho m naught 3/2 and p plus another constant, let's call it c3. So you get lambda is 3/2 is equal to 2/3 8 pi g over 3 rho m naught 1/3 and t plus c3 for 2/3. Okay, so up to an overall constant shift, it goes as t to the 2/3 in the matter dominant area. Okay, so let me now discuss how these various parameters are measured. So measurement of the parameters. So we start from the by writing down the Friedman equation again. Let me write in terms of lambda. Okay, I could have written in terms of lambda and a naught, but we don't do that because we really want the value today. Okay, because that's what we measure. So today, apply this formula today. So what is lambda dot over lambda? That's A dot over A. Today that's Hubble constant, right? H naught. So H naught square plus K over lambda square. Lambda is 1 today. So K over A naught square equals to 850 over 3 rho r naught plus rho n naught plus rho lambda. So H naught is measured from redshift. Right? As we discussed, if you know the distance redshift relation, we know how A is expanding, how the universe is expanding. From there we can measure H naught, and its value is between 60 to 70. Let me write down the result. I said what the units are. It's kilometer plus second per megaparsec. Megaparsec, okay, say parsec is 3.086 times 10 to the 18 centimeter, and megaparsec is 10 to the 6 parsec. What does this mean? This means that if you observe a body that is 1 megaparsec away from us, it would appear that that object is moving away from us at a velocity of 60 to 70 km per second. Okay, of course this is only on the average, right? You are not counting the individual local velocities of the body, so this is only after taking average, this is true. So 60 to 70 km per second of course looks like a big number, but you really have to go a very, very large distance away to have such big velocities. Okay, so in real time this is really a very small rate of expansion. Okay. And you can also see that this has a unit of 1 over time. Okay, why? Because it's kilometer, this is distance, okay, but you are dividing by megaparsec, which is also distance. So this is really 1 over the time, right? H naught has a measure of 1 over time, and we'll see later that this time that comes in the denominator is roughly the age of the universe, okay, T naught, what we have been calling T naught today. Okay, but right now of course we have not done that, but that is one of the significance of measuring H naught. Okay, the measuring H naught tells us about the age of the universe.
If some object is at a distance 1 megaparsec from us,
Yes,
then it from us at 60 to 80 km per second.
70.
70 km per second, yes.
If it was 2 megaparsec, then
It will be twice that.
oh,
Right? So, for small distances, the megaparsec in this limit is still a small distance. Okay? For small distances, it grows linearly. Okay? But of course, when the distance becomes large, you have to do a little more work. Right? You have to use that formula integral dt over at is equal to integral dr over 1 minus kr square. Right? So you have to look at that formula and see what it actually implies.
It's 3.086.
Yes, 3.086.
So why?
Basically, it was introduced by astronomers for very astronomical distances. Yeah, and it has remained. This unit is what is used.
So why this is increasing as we go further and further, because deaccelerate.
Why it's increasing?
Acceleration.
Acceleration. Not acceleration. The
Deaccelerate.
no, not it has nothing to do with the deceleration. Even if the universe expands at a constant speed, right? You see that it's at square let's take flat universe, okay? at square times dx square plus dy square plus dz square. Okay? Take the origin and the point r, distance r away, right? Suppose you are sitting at the origin. So then the physical distance of a particle located at r, okay, is r times at.
Yeah.
Right? So the rate of increase of the distance is r times a dot t. Right? So t is r times a t. So what should we call it? The physical distance, r physical. So d dt of r physical is r times a. A dot.
Okay.
So if r is doubled, then the rate of increase of r physical will also double. Yeah, that's the reason why it's linear.
So, equation h0 by a dot over a.
Yes.
So, if h0 we know is a constant value. If a increases, means we go to further distance. When a increases, then a dot should also.
Yeah. Not that a increases. See that. I mean, it does that. It's multiplying the physical distance is a times the coordinate r, right? So the rate of change of the physical distance is r times d dt, right? So if r is doubled, then the rate, the physical distance, it's like if you have a plane and if it's uniformly scaled down, right? Imagine that you have a plane and for some reason it's uniformly getting scaled, right? So these 2 points at a distance of 1 centimeter apart, okay, will move away at certain rate, but 2 points at a distance of 2 centimeter apart will move away at double the rate,
Oh yeah.
right? Because it is uniformly scaled down, right? This a of t multiplying it means that the metric is uniformly scaled down everywhere. And that's the intuition. The farther away it is, the faster it will move away from us. Is this point clear? Okay. So as I said, this h is measured from that relation, distance redshift. Okay, you see how far away the object is, how fast it is moving away from us, right? And that tells you a dot over a. So because 1 over r physical, d dt of r physical is r a dot of t over r of a, r times a of t. Right? Again, this formula is for k equal to 0, right? So where you can use this simple formula. So this is h, right? So if you can calculate the rate at which distant objects are appearing to move away from us and divide it by the distance of that object, you have h or h naught.
So any object or anything in the universe is not moving in the space. It is steady. No?
Yes. So, but apparently the distance is increasing.
Distance is, so if some matter is, if some star is there in the space, then the star is in the space at that position only.
Yes.
Only the space.
See, I mean when you say the star is in the space in that position only, it's a coordinate dependent statement, right?
Yeah, but that is not moving. No? That is steady.
In a specific coordinate system, right? In the coordinate system that we have used, right?
But
the
from this formula, when you are saying when there is distance, there that this rate of expansion is coming out. So if the distance is 0, means we are taking that matter itself. Means
no, the distance is physical distance, r physical, right? R times a of t.
So we can think of distance getting smaller and smaller. Physical distance
Yes.
getting small. So if it is very small, this thing means expansion will be slowed down.
Yeah, so the point is this ratio is fixed. This is the h naught, right? Just look at this formula. R physical is r times a of t. Okay? So d dt of r physical is r, of course, is you are keeping constant. Okay? In this coordinate system, you keep the locations of the objects constant. So d dt of r physical is r times d dt of a of t. Okay? So when you take a ratio, it's r a dot over r a, so this is a dot over a. So this is what remains fixed. This is our h dot. Okay?
But from this formula, it seems that if we standing here, if we look very far, then their expansion is getting very faster and faster. So if we are seeing closer, then their expansion rate is slow. With
No,
respect to our
expansion, okay, it depends on what you mean by expansion, right? It's a dot over e, a remains fixed. Okay? It is true that the farther away objects are appearing to move faster.
yeah, for us, but at every point it is true that
Exactly.
yeah,
So it is homogeneous, right? So every point. So it's like if you have a plane and if it gets scaled uniformly, right? That's what is happening, right? Just imagine that there is this plane,
okay.
right, is getting scaled uniformly, right? So 2 points which are further earlier will appear to move away faster, right? Because if 1 centimeter becomes 1.1 centimeter after a certain time, 2 centimeter will become 2.2 centimeter, right? So if this 1 centimeter away points are appearing to move further away by 0.1 centimeter, whereas the distance of 2 centimeter, they would appear to move away by 0.2 centimeter, right, in the same time period. Okay, but this, as I said, is a somewhat simplified formula. This is true only for not so far away objects, because this ignores, for example, that a of t itself would have been different in the past. Right? We are thinking of this. Imagine you have a constant a of t, right, where you can just ignore the variation of not a of t, the a dot of t. Okay, that's why you can ignore the variation of a dot of t, the deceleration or something. Think of a dot as constant. Okay. With that formula, this is true.
But this time is a universal time, right?
Pardon? Yeah, this time is the universal time, the cosmic time.
So whenever so if one is measuring such a thing, then they should use a universal time where.
No, you are using universal time. Okay, but it's just that if you look very far away, right? The a dot itself would have been different. A dot over a would have been different at that time. Right? So this is only taking into account the linear term. Right? I am assuming that this is constant, right? But that is not true in general. It is changing, right? So for very far away objects, this formula is not true. Okay, then you have to take into account the fact that there is an acceleration term and so on. Okay? But for nearby objects, sufficiently nearby objects, okay, when the linear relation, when the higher order terms are negligible.
So for us, nearby means how much? How
Oh, nearby means really far, right? In this language. 1 megaparsec is not very far in this language.
1 megaparsec, 3.0.
Light
How many
years.
light years?
We can calculate 10 to the 10, 3 times 10 to the 10 is
3.26.
like
3.26 right here.
so like we have to multiply by 10 to the 6. So it's there 10 to the 24, right? It's a huge distance.
Million light
Small.
years.
Pardon?
Still you are saying it's small.
Yeah, it's small from over the scale of expansion of the universe. The universe is much bigger, right?
3 million size.
Sir, you were saying this thing about rest, the objects being at rest, meaning in the sense that when I average over the local motions, then whatever remains is
Exactly. Because the point is, if this homogeneity and isotropy implies that on the average, the objects must be at rest in this frame, in this coordinate system. Right? Because otherwise, Tij wouldn't have that form that he assumed. Right? Ti0 equal to 0. Why? Because average velocities we assumed are 0 in this frame. Right?
So the average motion amounts to being 0.
Exactly. That's it. So this frame, right, is special in the sense that it is in this frame that the average motion of the stars is 0. Right? So when you average over all the nearby objects, you will get that.
So these all rotations and everything, they are kind of averaged over.
Exactly. That's right.
So the expansion mean only the scale factor that is increased. That means
Exactly. That's right. Okay. So you'll ignore the fact that locally each individual star or galaxy may be moving, right? But if one is moving this way, the other will be moving in the opposite direction. So on the average, that effect will should go away. Okay. There is one effect, of course, which should not go away that way. Okay. Which is that if we are ourselves moving in this cosmic time, okay, that we are not going to get it up by averaging over other stars, right? So they are going to determine this, right? And that is by finding our motion in the microwave background, which related to the microwave background. But we will discuss that later.
So in a way we want that our whole microwave background should be symmetric.
Yes, so the cosmic frame is the one in which the microwave background is isotropic. Right? Whereas what we see from here, the cosmic microwave background is not isotropic, and the reason is because we are moving through it. Right? If there is a black body radiation, and if we move through the black body radiation, it will not look the temperature is uniform in all directions. Right? And that's what happens, and that's how you can figure out what is our velocity in this cosmic frame. Okay, and we can correct for it.
So that motion comes due to some other reasons, or also due to this?
No, due to local fluctuations, right? I mean, we might have been formed by some explosion, right? And that radial velocity of explosion, some other objects are moving in the other direction, and we are moving in one direction. Right? So it's just that variation. Okay, so now let's go ahead. We have only discussed one parameter. Okay, now we are going to introduce a notation based on this. So what we are going to do is to write this equation by taking the h naught square in the denominator. So we first define a new quantity rho c, which is 3h naught square over 8 pi g. Well, I should have told you, I think the current waste value is about 67. Okay, but this fluctuates from year to year, depending on the measurement, but it's getting close, right? Within plus minus 1 kilometer per second per megaparsec, we more or less know what pi g, and you can check that this has a dimension of density. And we can calculate it, because if you know h naught, of course, we can calculate it. So if you take for h naught equal to 65 kilometer per second plus megaparsec, I think we get rho c of order 8 times 10 to the minus 30 gram per cc.
So what this is called? This rho c.
Critical density. This is called critical density. So this equation now can be written in slightly different way. K over h naught square v naught square. I divide by h naught square, and then I take this one that appears on the right hand side. So this becomes 1 over rho c times rho r naught plus rho m naught plus rho lambda naught minus 1. Minus 1. 3h naught square over 8 pi g is our rho c, so that comes in the denominator, right? And then I take this minus 1 on the other side. So from this we see that rho c is already given. Right? So if you know these quantities, we can calculate k over a naught square. Right? So that is basically the way k over a naught square is determined. And now you see that earlier you had said that rho's are very small, right? Okay. Indeed, the density of matter, okay, or radiation is very small in today's universe. Okay. But the relevant quantity that we should compare it with is this rho c. Okay, that is very small. Okay, so this number could be order 1. Okay, and in fact it is of order 1.
So this number, so this ratio is what of the order of 1?
Yeah, so we will give the values of now the ratios, and we will say they are all of order 1, right? So even though the densities look very small, in the natural scale, okay, these densities are actually not very small, right? Because rho c is so small. Okay, rho c is so small because h naught is very small, right? So you can say g has come in the denominator, right? So indeed g is small, but h naught basically compensates for it. Okay, so in CGS units, rho c is a very small density. Okay, let me start with rho m. Oh, maybe I should introduce another notation. Okay. So basically, one introduce the notion of omega I, which is rho I over rho c, where I is matter, radiation, or cosmological constant.
Why or why not?
Rho I naught. Rho I naught. So this is a constant. So you can also write this as k over h naught square is a naught square as 1 over omega r plus omega m plus omega lambda minus 1. So one thing you will notice is that in terms of physical quantities, what appears is always k over a naught square. Right? This is what you can calculate. You cannot calculate k directly by any means. Okay, at least by this kind of local measurement.
So still we can get estimation of k by, because we have seen earlier that only k equals to 0, 1 and minus 1 is possible.
Yes.
So if this is positive, then k is 1 and
Yeah, that's true. But what I'm saying is that, I mean, really, even though we wrote it that way, right, in all physical formula, what enters is k over a0 square. Right? So that's really what we want to know. Okay, and if k over a0 square is very small, right? Suppose it's close to 0, but we don't know what its sign is. Right? It's not relevant, okay, to actually know the sign to study the physics, and the reason is that k over a naught square being very small basically means whether it's a sphere or a hyperbola, it is very flat. It's very big radius, right? A sphere of a very big radius, okay, from local perspective is indistinguishable from a plane. Right? Similarly, a hyperbola of a very big radius, okay, is indistinguishable from a plane. Okay, and that's what we are saying. That is a physical fact that's appearing in this equation, right? That you always get this combination which is important. Okay, so omega n. Let's start with the calculation of omega n. So omega n requires measuring rho m and then dividing by rho c, right? Rho c you already know, so you have to calculate rho m today. So the most naive calculation, okay, which is that you just collect all data about luminous matter, right? The stars and galaxies that you see, okay, and then you make some estimate of what kind of dust may be there in between the stars and so on. Add them up, okay, from just from observation. That gives a result for omega n, which is of the order. So direct observation gives 0.04. Okay, which is really small compared to the critical density. Okay, so this is the omega n. Okay, so omega n However, it turns out that there is more. And the way we see there is more, okay, is the following. Okay, now there are of course various other ways, but this is one of the standard ways that this discrepancy was discovered. So let's suppose that we have a galaxy, okay, and we look at the motion of stars which are near the edge of the galaxy, okay, which are revolving around the galaxy in some orbit. Okay, let's take circular orbit. So then, over this scale, Einstein, the Newton's theory is good enough, at least in as a first approximation. So you can just apply Newtonian mechanics, and we conclude that the way we determine the orbit is that you equate the centrifugal force with the centripetal force. Right? Centrifugal force you balance against the gravitational attraction. So you have Gm m over r square. This is the mass of the galaxy. Is equal to mv square over r. So this is the mass of the star, and this capital M is the mass of the galaxy. So this gives a formula for V, which is square root of Gm over r. So what one expects that if we observe several stars near the edge of the galaxy at various distances and plot V against star, it should fall off as 1 over square root of r. Okay? But when you actually plot V versus R, one basically finds a plot like this. Yeah, as if it's asymptote, so some constant. So what can that mean? That can only mean that this M somehow is growing with R. Right? That M is proportional to R. However, if you actually look towards the edge of the galaxy, right? Basically you don't see any stars or anything there. Okay? So you cannot account for this M growing as linearly with R, okay, just from the known matter. So this tells us there must be something in addition to what we see. Right? Just from what we see, okay, and then extrapolating a bit, we cannot figure out correctly how much mass is there in the galaxy. So this is what is called dark matter, okay, which is not observable directly. Okay, but whose presence is known because of this indirect measurement of the rotation curve.
So the galaxy is a continuous distribution of stars.
Yes, that's right. But it's a continuous distribution, but the stars are concentrated somewhere in the middle, and then slowly the density dies off, right? And this observation is made in the region where the density has died off. Okay, near the edge.
Few stars are there.
Pardon? Yeah, few stars are there, exactly. Okay? Towards the edge of the galaxy. Okay, that's how you plot this curve, and this is what you find. Okay? And this you cannot account for the few stars which are there near the edge of the galaxy. Okay? So you really have to conclude there is something there that you don't see. Okay, and this is what is called dark matter.
We have measured the velocity of the stars at different radiuses.
That's right, exactly.
Okay, so all are on the edge.
All are on the edge, exactly. Because in the interior, of course, it depends on how much mass is inside, right?
Yeah.
But so that's why you look near the edge. All are so this part is not really relevant, right? That we don't expect that this formula will hold for smaller. You just look at larger. And what you find in the larger region, instead of falling off as 1 over root r, it becomes a constant.
So, but if you will be some limit after which it should fall. Because
Yeah, certainly.
if you keep on increasing.
I agree, yes, right. But what it is saying is this matter is extending, right, beyond what you see. Okay. And then there are various other experiments that one can do to estimate how much of such matter is there.
The distribution of
Yeah, that how much matter, okay, of this kind is there, okay, which is required to account for this kind of rotation curve.
Up to what distance they see this?
Basically, they see it to a long distance, much beyond the radius of the galaxy.
This behavior is when the stars are actually inside the galaxy, that we should take the mass terms as important.
Yes, so the stars are not, of course, the stars are at the edge of the galaxy, right? I mean, outside the galaxy there is nothing.
Yeah, they are looking like they are at edge.
Yeah, so you have to look at the edge. They are looking like they are at the edge. Okay, but what it is saying is that they are cannot. It's not really the edge. Okay? It's not that the mass density is uniform, right? Because total mass is growing as r, meaning actual density is falling off at 1 over r square. Right? Because 4/3 pi r cube is the volume, right? That's the volume. Okay, so density is falling off, but it's not falling off as fast as you see. And using that, you can estimate how much of such extra mass is there. Okay, there are various other experiments, but this is one of them. Okay, which indicated that there is more matter than what you see, and this is what is called dark matter. And the current theory, although nobody has actually figured out what exactly it is, is that these may be some new kind of particles, okay, which do not interact with visible matter. Okay, at least which are very little interaction with visible matter. That's why you don't see them. Okay, but some kind of elementary particles floating around in the universe.
R equals to 0.
Because the point is that near the origin, right? As you go farther and farther away, there is more and more mass inside. Right? So initially, the fact that the mass will grow as a function of r, of course, is not surprising, right? Because near the origin, of course, there is nothing.
High density.
Yeah, even if it's uniform density, total mass enclosed will grow as r cube, right? Because 4/3 pi r cube is the volume enclosed, right? If the uniform density, m will rise as a r cube. Okay? So this dark matter clearly is saying that m is not rising as r cube. Okay, so it's not uniform density of dark matter that you are saying. Right? The dark matter density is falling off near the edge. Okay? Nevertheless, it's not falling off as fast as you have seen. Okay? Because according to the observation, the density has become almost zero. Okay? That certainly hasn't happened because of this rise in the curve. So the upshot is that once you estimate the total dark matter density, you find that omega m is about 0.27. Okay, this is I think the current base value of omega m. Okay, so this basically shows that the most of the matter in the universe is really dark matter. Okay, the observed matter only accounts for a small fraction of the total matter. Okay, now let me come to rho r. So omega r.
Then this is all your treatment equation considering only 3 contributions, right?
Yes.
So how is this analysis compatible actually? You have taken the contributions only from 3 kinds of sources. Now
Yes.
this inconsistency shows that there is a 4th kind of source.
Yes, there is a fourth kind of source.
So doesn't it like fall back upon how you actually formed the Friedmann equations in the first place?
Yeah, so the point is, you can ask, this dark matter, no, Friedmann equation was written as a sum of rows, right? So you can ask that this dark matter may have an equation of state that is different from what you have used.
yes.
See, if its equation of state is that of matter, then you can dump it with the ordinary matter, right? So now you can ask that could this dark matter have some other equation of state? Right? And so that of course is not directly obvious from this analysis, right? But people have, tried various equations of state, right? And basically based on simulations and so on, now we know that the best candidate for dark matter is really non-relativistic matter. The same kind of matter that we see in the universe.
Then here you have done an approximation in which, like in the Newtonian approximation, right?
Yes.
Those approximations are matters are the one which actually creates anything like radiation.
No, radiation will also you can okay, it's Newtonian, but nevertheless, so you can okay. The point first of all, you can of course correct for it, right? When you actually look for what is the equation of state for dark matter, right? You will use the full relativistic equation, right? But nevertheless, the fact remains that just this analysis cannot tell us that definitely that the matter that we are seeing is non-relativistic. Right? It just says that there is something more. Okay? It cannot tell that it's non-relativistic. Right? That requires more effort to figure out. Right? In fact, in the initial days, people didn't know. Okay? People tried what are called hot dark matter, right? Which are highly relativistic particles moving around. Cold dark matter refers to non-relativistic particles. And then also something called warm dark matter, where the velocity is not too low compared to C, but it's not very high compared to C either. Okay. So all of this has been tried, but now the best possible scenario, which basically explains a lot of the experimental data, is that this is really non-relativistic matter.
Okay, so left hand side doesn't change. It's just that if at all the kind of equation state was different, you would have added a fourth contribution to
Exactly, that's right. You would have added a fourth contribution, right? Which will have a different dependence on A. Right? Instead of having falling off as 1 over A cube, you will have a different fall off. Okay. So radiation, omega r. So this basically comes from the cosmic microwave background.
And so those lights and other radiations from the stars and galaxies?
Those are very small. Okay, those are not relevant for this calculus because cosmic microwave background basically fills the whole of space, right? Even space between the galaxies, okay, or galaxy clusters. So this certainly dominates over everything else. Okay. So this basically is a 2.7 degree Kelvin black body radiation. And so now we can calculate the density from the black body radiation formula. Okay. So density goes as some constant times T to the 4. This is some known constant. So you can calculate the energy density of this radiation, and from there you can calculate omega r, because omega r is just rho r over rho c. So this gives you a value of omega r, which is small. It's 5. Omega r is about 5 times 10 to the minus 5. Now this is not completely true, not because of any direct observation, okay, but because of some theoretical reasoning, okay, which comes when you actually follow the history of the universe from high temperature. The photons are of course what you observe, right? This black body radiation from photons is what you observe, but if you calculate the evolution of the universe theoretically, you also find that there are neutrinos. Okay? There should be neutrinos, okay, which also have black body spectrum, okay, but at a slightly different temperature. Okay? So neutrino, pardon?
So we assume need to know obey that radiation equation of state.
Yes, because if they are massless neutrinos, right?
Assume
If the
that-
neutrinos are massive, then the equation of state will change, right? Again, early in the universe, when the temperature was higher than the neutrino mass, it's really radiation. Okay. As it evolves, it becomes. You can think of this as matter.
And also we can neglect the mass because it's very small.
Yeah, except that if the temperature, whether you can neglect the mass or not depends on the competition between the kBT, right, the Boltzmann constant times T, that's the average energy, and the mass,
Okay.
the rest mass energy, right? If kT is larger than the rest mass energy, then you can neglect the mass, then it's like a radiation. If kT is much smaller than the rest mass energy, then it's like a non-relativistic matter. Okay? That's the rule that you have to follow.
Okay.
Okay, so basically neutrino, what you can argue, okay, again this is, I am just stating, it certainly doesn't follow from any direct experimental observation, right, because we don't observe neutrinos at circular temperature. But what one can argue is that neutrinos have temperature which is 4/11 to the 1/3 times 2.73 Kelvin. Okay, this 4/11 to the 1/3 comes from high energy analysis. Okay, as I said, this is a prediction rather than an experimental observation. So anyway, so this doesn't change things very much. What it does effectively is that it multiplies this by a factor. So one is the photon contribution. Okay, the factor that you multiplies it by is 3 times 7/8 times 4/11 to the power 4. So this 3, because there are 3 kinds of neutrinos. 7/8, it's the difference between bosons and fermions. Okay, in the formula for the energy, okay, there is a factor of 7/8 for fermions, and this is T to the 4. Okay, if the temperature goes as 4/11 to the 1/3, then temperature to the 4 gives you this.
Can you write it again?
Write it again, okay. So
What is that? 1 plus?
I'll write it. So basically omega r total is omega r electromagnetic. Okay, this is what we observe. Times 1 plus 3 times 7/8 times 4/11 to the 4/3. Okay, so this is the contribution from the photon, and this is the contribution from the neutrino. The 3 because of 3 neutrinos, 7/8 because neutrinos are fermions rather than bosons, and this 4/11 to the 4/3 because of the temperature difference. But this is in any case a number of order 1, right? That's what is important. So this is not going to do very much. It still remains like 5 times, maybe of the order of 10 to the minus 4. Okay. So it's still negligible today. Let me try to give the determination of rho lambda, and then it will become, then that's it. Okay. So now omega lambda. This is indirect. So you cannot directly measure cosmological constant as mass because essentially because it has really no effect on very much on direct observation. So this starts from study of the Friedmann equation. Okay, so A dot square. This is again slightly different to writing the Friedman equation. Normally write as A dot square over A square. Now I'm writing A dot square. A dot square is minus K plus 8 pi G over 3 times rho m A naught cube over A plus rho R naught A naught to be 4 over A square plus rho lambda naught A square. Okay, if I divide by A naught, just lambda dot square, then you get back 1 over lambda cube, 1 over lambda to the 4 and lambda square. Okay, it's the same formula that we wrote down. Okay. So the idea is that we take d dt of this equation on both sides and evaluate it at t equal to t. Okay, just take the derivative on both sides and set t equal to t naught, right? So you get A double dot on the left hand side. So you get A double dot over A at t naught is 4 pi g over 3 2 rho lambda naught minus rho m naught minus 2 rho r naught. Okay. These are the given exercise. Basically these 2 minus 1 and minus 2, they come because you see, if you take a ddt of this, you get a minus 1 because there is a in the denominator, right? It becomes minus A dot over A square. Here you get a minus 2. Minus 2 A dot over A cube. And this gives you plus 2 A dot A, right? That's what these strange numbers are coming from. Okay, what are these? I'll take as an exercise. Now let's compare this with our definition of the deceleration parameter. So recall that we had defined the deceleration parameter by saying that AT over A naught is 1 plus H naught T minus T naught minus half Q naught H naught square T minus T naught square, and then plus higher order terms. That A double dot over A naught is minus Q naught H naught square. Is this clear? Now, as I told you last time, Q naught is now measured. And this was what was measured by this supernova cosmology project. So Q naught is known. If Q naught is known, that means this combination is known. Right? Because everything else is known. H naught, of course, is known. Okay. So Q naught tells us 2 rho lambda naught minus rho m naught minus 2 rho r naught, and hence also tells us about 2 omega lambda minus omega m minus 2 omega r.
So
2 omega lambda.
2 omega n.
No, this is just rho m naught.
Oh, yes.
So just minus omega m, right? Because we are just dividing by rho c. This whole thing. Right? Rho c is already known, right? 10 to the minus 30 gram per cc, right? That I wrote down. So you just divide by rho c to get the omega, this combination of the omegas. Is it clear? Okay. So this you go from here to here by just multiplying by 1 over rho c. Now omega m and omega r have already determined. Okay, we have discussed how to determine omega m and omega r. So if we know this, we can calculate omega lambda.
So there is a minus.
There is a minus sign.
Because
Well,
Q
I
naught
just
is negative.
yeah. So I just said Q naught implies this, not that Q naught is equal to this, right? Or I said that if you know Q naught, that yeah. So the point is that because Q naught is negative, we know that this is positive. Right? Because you see that this is minus Q naught H naught square, right? And here you have this factor. So a negative Q naught cannot be explained by these. That's clear. It was also clear from the diagram that we drew. Right? An acceleration is impossible to explain if the potential is rising. Right? The potential has to fall, and that can only happen by the cosmological constant. Okay, you again see this from this formula. Okay? If Q naught is negative, that means if the universe is accelerating, it better be that this is non-zero.
Yeah.
Okay, but here you have more. Knowing the value of Q naught, you can actually determine partitions. Okay, and these are all known, and hence it determines omega lambda. Okay. That is of the order of 0.73. So now we go back to our formula, old formula, K over H naught square A naught square is omega r plus omega m plus omega lambda minus 1. This is of the order of 10 to the minus 4. This is about 0.27. This is about 0.73. Okay, so you see from here that this combination is almost zero. In fact, so far within error bar of experiment, it is zero. Okay, there is no experimental signature that is different from zero, and that basically shows that K over H naught square A naught square is very close to zero. Okay, what is important is that it's much smaller than any of these components. Well, it is much smaller than these components, omega and omega lambda. So, right? We cannot really say it's smaller than omega r today, okay, but at least it's much smaller than omega and omega lambda.
What you're calling omega includes the dark matter contribution as well.
Yes, yes, it includes the dark matter contribution as well. Okay, otherwise it would have been 0.04, right? So this 0.27 comes by including the dark matter contribution.
0.23 is dark matter.
Yeah, 0.23 is about dark matter, yes.
So if there were no dark matter, the cosmological constant,
Yes.
then it would have been negative always.
Yes, exactly.
Large
Then K would have been now minus 1. Okay, so this then explains why we can effectively set K equal to 0 for studying cosmology. Okay, at least for present cosmology as well as far in the past and far in the future, K over A square term never really becomes important. Right? It's always the other terms, one of the other terms is dominating. Is this clear? Okay, so I'll stop here, and then next time we will discuss more about the temperature, because this is more or less all you can do with just gravity. Okay, if we didn't know anything else about the system, right? All you can do is we have today's data and we evolve it backwards and forwards, right? Assuming that there is no energy exchange or anything. But this, of course, is not a real story, right? And as you go far in the past, right, this microwave background which is there, its temperature would have been much hotter in the past. And then it would have interacted with matter significantly, okay, and things would have been different. So we'll be studying part of that at least next time.